Hi everyone, and welcome to this video. We're going to talk today about constructing space-time diagrams and then looking at what happens when we include multiple frames on one set of axes. That sounds like a lot, but actually it's a lot simpler than you might think. However, a video might just be helpful to process those ideas. If you need to pause at any point, please feel free to do so. So let's talk about space-time diagrams. Really, a space-time diagram is a different version of something that you've seen before. Okay, we're really looking about how space and time relate to each other. We're going to refer to space as x and time as t, and those should be two coordinates that you're familiar with from your mechanics. Now, there are some little tweaks which we need to go through, so let's just go for it. Firstly, when we're drawing a space-time diagram, we are representing what we call a reference frame. In other words, a point of view. Okay, and as we've done in previous relativity topics, we'll be talking about multiple points of view and how those interact with each other later. Now, when we're constructing a space-time diagram, what we tend to do is we plot the x, the position, the spatial position, x on the x-axis. Okay, that's different to your, for example, displacement time graph, where this might be on the y-axis. In this case, we're putting it on the x-axis. Okay, we then put what we call the temporal coordinates. So temporal means time here, ct. Okay, so this is going to go on the y-axis. Now notice here we're using ct, not time, okay, but the speed of light, c multiplied by the time. Okay, there's a few reasons for this. Okay, you will have learned about the space-time interval and how this is calculated. Basically, what we want to do is have the same units on both of our axes. And so here we've got c times t, that's speed times a time. So that will give us something in units of length, length against length there. Okay, so this is usually measured and plotted as c times t. Okay, now the reason that we use spacetimes is that we're able to follow the paths of certain objects, determine the time between events, etc. And we often sometimes use the word world line. Okay, now world line is a line which shows the path or trajectory of an object within this space-time. Okay, and if our world line has a straight line, it has constant speed. This is again the same for our displacement time graphs, where we have a straight line. That would mean constant velocity. Now, one particular world line that you need to get used to drawing is a line at 45 degrees. Okay, this shows the world line of an object traveling at the speed of light, c. Okay, so this green line you can see there is the world line of light. And what that basically tells me is if my light started at position 0, x0, time 0, then it's going to follow that trajectory that you can see on the screen. So that's basically how we construct our space-time diagrams. Okay, very simple initially, but as ever in physics, it's going to get a little bit trickier. So feel free to pause and have a think, take any notes you need to before you move on. Okay, let's move on. Let's talk about what happens when we want to include multiple frames. So currently we're looking at the x and t or x and ct coordinates. Okay, well, it's possible on a space-time diagram to start looking from different points of view, from different reference frames. So let's imagine we have an observer S primed, which is moving relative to S. So S is our rest frame and S primed is our moving, and we've got speed v as usual. We can represent the coordinates as measured by the reference frame S primed by using our different nomenclature, which is x primed and ct primed. Okay, again, you'll be familiar with the primes from, for example, Lorentz and Galilean transformations. Okay, how do we represent these on a space-time diagram? Well, it's quite simple. All we do is we draw two more axes. And we label them ct prime and xt prime, but notice they are tilted. Okay, these axes are tilted towards that light world line that you can see on the screen. And actually, the faster that we go, the more that they're going to approach light. And that kind of makes sense, because if that's the world line of light on our screen, we're going to expect, as we go faster, to approach that speed of light. So we've drawn two axes here. Okay, remember right now all we're doing is thinking about to construct this, not necessarily how to use the space-time diagram. We've got two axes with the same origin, and they're both oriented at an angle theta to both ct and x. So that angle there should be the same. Now, there is a way of calculating the angle, and it's related to the speed. I've just said that if we went faster, we expect our lines to approach the world line of light. And so in this case, we have a relationship which is tan of theta, okay, which is equal to v divided by c. In this case, again, c is the speed of light. So you can see there, the faster we go, the more we approach higher angles, and therefore that kind of makes sense. Okay, so again, this is just about how we construct the space-time diagram. What we're going to take you through is a couple of questions just to make sure that we're all okay with how these multiple frames are relating to each other, and then we can think about how to use the space-time diagrams in a slightly more informed way. So let's try a couple of questions. Okay, let's imagine, for example, that we could prove that if theta is 45, then the relative speed between the two frames is going to be c. It's going to be equal to c. So let's have a think about that. Feel free to pause the video at this stage and try the question on your own. Okay. I'm assuming you've had a chance to have a try of that. We know that tan theta is v over c. Well, if the relative speed between the two frames is c, well, that means that v is equal to c. C over c, that just gives you 1. Inverse tan of 1 is 45 degrees. Okay, so that's why we write that that world line of light as being at a 45-degree angle to the both the ct and x-axes, and that kind of makes sense because it should be symmetrical, and the most symmetrical there would be 45. Okay, let's try another question. We could calculate the relative speed between two reference frames if theta equals 30. Again, feel free to take your time. Okay, let's go for it. We've got tan of theta is equal to v divided by c. Tan of 30 is going to be v over c, which is 0.577. And there we go. We know there that v is equal to 0.577 times c, which is going to give us a rough value of 1.73 times 10 to the 8 meters per second. You sometimes could express this as 0.577 c as well. That would also be fine. Okay, and finally, we've now got a spaceship S primed, which moves at speed 180 million meters per second relative to S, and we're asked to calculate the angle between the two axes. Again, we can do tan theta is equal to v over c. Tan of theta is equal to v, 180 million, over c, 300 million, equals 0.6. And that will give you a 31-degree angle. Okay, take your time to think about those concepts, make sure you update your notes, etc., and then we can try a couple more problems in our lessons. Thank you for watching.